And
Sir, I attempted that class.
okay, so you had I mean total clarity over whatever was discussed in there.
Yes, sir.
Okay, so I'll start today's session. Let's hope people join in the meantime. So if the audio and video is not clear, you can unmute yourself and speak. So my name is Shutanu Sadhukan. I am a teaching assistant uh, of NPTEL PMRF TAship, and I'm a PhD scholar from IIT Bombay. Here my Twitter, LinkedIn, and YouTube handles are there where the videos will be uploaded, and you can connect me always later if you have any doubt. So this was the tentative overview of the Tuesday evening sessions. Those will be occurring uh, in the event semester of 2024. And I welcome you all for the interactive session of week 2 of water and wastewater treatment. The course code is C39. It is offered by Dr. Bhanu Prakash Belanki, who is an environmental engineer from IIT Roorkee. So where are we? We are at the second week. The previous recordings has been uploaded. All the 3 years has uploaded their recording. If you have not watched them, go and watch. And also I will again share you some unshare my screen, and I'll just told that in the last class the way you can access the recording I'll show you. So that's why I'm just sharing again my screen. So let me share my entire screen. Okay, now in your Swayam portal, if you go to my courses, so there you will see under the title water and wastewater treatment, if you just go to the course, the forum link is also there under the ask a question button, where you can ask a question if you have any doubt. And at the left hand side, at the bottom left corner, you will be seeing the problem solving session of January 2024. Just click on that and click on the recording. Then if you just click here in the other tab, and Excel sheet will come out, where you will see the presentation link. The presentation folder is also there, where whatever the presentation is being done, that will be uploaded in the folder by TS, and the recording will be uploaded here at the under the YouTube link column. So I hope it is clear. And okay, so we can start our usual session. Let me close these things. Okay, so let me again unshare and reshare my screen. Okay, so today's session we will be starting with a 2 minutes video. The video is based on the 1854 Broad Street London cholera outbreak, and it is taken from this channel. Okay, so let's play this and watch this together. If the audio is not audible, then you can unmute yourself and speak.
In 1854, cholera struck the city of London. Over 600 people died in just a few weeks. People thought that when there were terrible outbreaks of disease, especially cholera, that it was caused by poisonous air. But John Snow, the physician in London, was convinced that cholera in particular was a waterborne disease.
He was an icon of epidemiology. Yeah. He was against the flow of the times. What was very interesting about John Snow was the deductive reasoning. He was very much a scientist, and he believed in measurement.
As the father of epidemiology, he got on his feet and walked around and started asking, where are these illnesses occurring? So he could see patterns. Epidemiologists essentially look for patterns of disease and then make a prediction of the causes or origins of the outbreak.
And right here was the Broad Street pump. And it turned out that most of the people who had fallen ill and who were continuing to fall ill had drunk water from this particular pump.
John Snow is often credited with ending the 1854 epidemic by removing the handle from the contaminated Broad Street pump. The full story is much more interesting.
So that's it. We all know about Dr. John Snow. I think you have watched Sar's lecture. The video is about how he prevented it, but some certain experiments he did on the contaminated water, though he was not able to determine what was the actual cause, that is, what is the component that is present inside the water for which the cholera outbreak is occurring. But he indeed, people were thinking that it was due to water pollution, due to air pollution, but he determined that it was due to the water pollution. But the presence of cholera bacteria that was not found at his time. But anyways, he actually used certain methods for the disinfection of the contaminants, whatever that is present inside the water, and that is causing the problem in the digestive system. So what he did, it is something like so couple of questions after this video, couple of questions will be based on whatever he did actually. So let's continue. Sorry. So the first MCQ is, what is the type of the compound that was used by Dr. John Snow to purify water during the outbreak? So you have to select the correct option. If you can answer if you have watched the lectures that was delivered by Dr. Bhelanki. So option A is oxidizing. The compound was an oxidizing agent. Option B is reducing agent. Option C is the compound was a biological agent, and none of the above. So you can type your answer in the chat box. Oxidizing agent. Okay. So I'll go with the answer. Yes. So Archana, you are correct. It is an oxidizing agent. Oxidizing means the agent basically donates electron during its chemical reaction, right? Or if it is an element, then it lies at the right hand side of the periodic table. So if you had a chemistry background in your +2 level. Okay. Now the next question is, which one of the following compounds was used by Dr. John Snow to purify water during the same outbreak? So it is again an MCQ, and you have to select the correct option. So option A is fluorine, option B is chlorine, option C is bromine, and option D is iodine. You can type your answer in the chat box. And Progyan and Orchana, both of you can just unmute and say your background. Okay, Orchana and Progyan both are saying it is chlorine. So you just two of you are there, so you can just unmute yourself and speak about your background. So from uh, what type of, I mean, uh, what is your educational background? I mean, you did your bachelor's or master's, or you are just finishing your school education and you are in colleges. So you just, Orchana, please go ahead.
Sir, I had completed my,
Yes, please.
sir, I had completed my post-graduation MSc from Environment Science
Okay,
in 2020.
okay, 2020. Okay. So, I mean, you had science background in your plus two level. Anyways, so I
Yes,
can keep my discussion accordingly. And Program, please go ahead.
Environment Science.
Ah, yes,
So presently, so
yes.
presently I am pursuing my bachelor's degree in civil engineering.
Okay, okay. So both of you had science background in your plus two level. Anyways, for the recording sake, as this is very
Yes, sir.
okay. So as this is very basic discussion, actually the course is meant for people from a diverse background and also from non-science background also. So if someone is taking the course, they will be able to understand. So it will be trying to balance both ways. Okay. So now let's go to the so let's see the answer. I think both of you have answered it correctly. It is chlorine. Okay. Now there is a table and you have to match the type of treatments which is in the left hand column with its primary with their primary functions which is there in the right hand column. So in the left hand column there are preliminary treatments, disinfection treatment, primary treatment and secondary treatment. These are all different types of water treatments and their primary functions which are stated as removal of pathogens, removal of suspended solids. Option C is removal of bigger sized particles and option D is removal of organics or BOD. Now, the removal of pathogen we basically saw in the last video and also subsequent questions. We saw that the scientist whose name is Dr. John Snow, he used uh, chlorination method for the disinfection of the bacteria that is present in the water and was causing the cholera outbreak. There are also other types of disinfection methods which are suitable in different cases, just like chlorination. So there are also ozonation, there are also UV treatments. So these are certain other popular techniques for the removal of pathogens. So you can match the columns and you can just type the, okay, you are saying 2 with A. Okay, so disinfection, yes, it is true. And also the preliminary, primary and secondary one, you can match like that way. You can just write the right hand order. So what will be the ABCD, what will be its correct order, you can just write that. Okay, in the meantime, for your information, I will tell certain other things. You see, there are chlorine actually how it removes the pathogen from the water. Actually, it forms a free radical, and with the help of that, actually it destroys the cell membrane or cell wall of the bacteria, and it disinfects of the water if the pathogen is present inside the water. And chlorine has got certain advantages and disadvantages. So chlorine is suitable for chlorination is suitable for countries like India, where after the water is pumped from the municipal or other sources after treatment, it goes via different various kinds of networks, and these networks actually, I mean, flows through various places, underground or whatever. So if there is certain leakage in the pipe, and then pathogen can come into the water. So after the treatment, if the pathogen comes into the water, chlorine has got an effective action because chlorine has got higher life. So otherwise, I mean, once the disinfectant gas is injected inside the water, it may come out, right? But the chlorine stays in radical form in water for longer period of time. So that's why it is suitable for developing countries like India. But the presence of chlorine in the water is not good for health. So once it reaches your home, it should be, I mean, it should be removed from the water. That's why what happens during you take a bath in swimming pool. So in the swimming pool, there actually there is chlorine present inside the swimming pool water, which is harmful for your hair. So that's why swimming caps are advised to wear. So that's why, so that the chlorine does not come in contact with the hair, and it does not lead to hair fall. So that's why. Another way of removing pathogen is ozone treatment. So ozone has got shorter lifespan inside water than the lifespan of chlorine. But ozone is more effective way of removing the pathogen. In countries like Finland, Norway, Sweden, etc. So the northern European countries, or the cold countries, and also where the population is not much more. Uh, I mean, where the water supply can be limited within a certain within a smaller region than the cities of India. So there the ozone treatment is more suitable. But the presence of ozone in water is even more harmful than the presence of chlorine inside the water during your consumption. So but it has got a shorter lifespan, so it is suitable for where the pipeline length is not very high. And another way is UV treatment, which is generally used in industrial waters. For example, if there is product and the water is used inside the reactor for making the product, then what may happen, there are biofilms present inside the pipe if there is a stagnancy. So before and after any stagnant region of the pipe, there are generally UV treatment, or UV lamps are stationed. So UV lamps also actually destroys the uh, bacterial cell wall with its I mean high radiation or whatever. And also it also modifies the genetic material of the bacteria, and by this way it actually disinfects or removes the pathogen from the water. Okay, so now let's see what you have told. So Archana is telling the order as CDBA, and Program is telling as CABD. Okay, so the first one is and the third one you are saying your answers are same, and option B and D you are saying differently. Okay, so let's see what is the answer. So the so actually the disinfections, that is you are linking 2 with A. So Progan has told this one correctly. So that the order Progan has given, that is correct. So the preliminary treatment is used for the removal of bigger sized particles. So what is the example of this type of treatment? There are bar screens, fine screens, which removes the visible, uh, just like phool patte bagara. So it removes those type of bigger
Yes,
particles.
like sedimentation.
Yes, yes. So those type of treatments actually removes the visible, whatever the particle that is visible in the water, and it can damage further treatment equipments also. So these are preliminarily removed from the water, and also sometimes sand filters are used, which are backwashed and regenerated like that way. So in this way, the preliminary treatment remove the bigger size particles. The disinfectants is related with the removal of pathogens. It is, I mean, I think it needs no further explanation. The primary treatment uh, is used for the removal of suspended solids, and the secondary treatment is used for the removal of organics or BOD. So we will come in this BOD later. So one thing we can say that there are three things we studied in our plus 2 level. Just for our recapitulation, I will tell that uh, there are three things. One is non-dissolved particles, colloidal particles, which are basically suspended, and the uh, dissolved particles. For example, sugar or salt, which are basically dissolved in water. What is the particle size? So the particles which are not dissolved in the water, they have got size bigger than 10 to the power minus 5 meter. The suspended solids or colloids, which are uh, you can say these are not dissolved and not dissolved. So these are in between. So their particle size is in between at the micron level, that is 10 to the power minus 5 to 10 to the power minus 7 meter. And the particles which has got their particle size less than 10 to the power minus 7 meter, they actually enters the intermolecular gap of water, and they are basically dissolved, and their particle size is at the nano range, nano or let's say angstrom range. So just like sodium chloride, these type of salts, they are basically completely dissolved in the water. So just if you keep the particle size in mind, then it will be easier for you to understand that the treatment scheme, if the preliminary, primary and secondary, all the treatment schemes are replaced with membrane. So the membrane pore size is adjusted according to the particle size. So we solved a problem regarding membrane treatment in the last class. If you go and watch the recording, you will be able to understand that. Okay, so now let's go to the next problem. So it is an MCQ, the MSQ, that is multiple select question. So nowadays, if you have given, so I see Procan will be giving the GATE exam, and Orchona maybe you have given the GATE exam. So they are nowadays, previously it was not there. Now they are actually asking MSQ. So there are multiple select type of questions. If you are giving all the correct answers, you will get the full marks. Otherwise, there is no negative marking, but there is no partial marking also, just like JEE Advanced. Okay. So this question is goes like this way. To select the pathogens that or those can effectively be removed by a typical sand filter. Option A is viruses, option B protozoa, option C worms, and option D bacteria. So you can type your answer in the chat box. Sorry. No other people is joining today. I think only you two are there. Yes, any doubt you can ask. Or for the recording sake, I will tell also for other people who will be watching the recording later, that you can uh, always ask the question in the forum. Even if you come with certain doubts, you can ask the question in the forum, and the NPTEL team or me along with the other TAs will try to answer your queries. Okay, so Progan is telling option A, B and D. Viruses I think are very fine, so I don't know, maybe they will not be effectively removed by sand filter. Okay, let's see what is the answer. B and D uh, that can effectively removed by a sand filter. I think you have assumed it incorrectly. I think you have assumed it as can't effectively. Welcome Shaikh, Abiba and Santosh Kumar. We just So you can watch the recordings if you have not watched it. The previous class, if you have not watched, then you can watch the recording later. And this class also, whatever you have missed half an hour, you can watch the recording later. Okay, and also slides will be shared, so no worries about that. So you two also try to answer the question. So which one or more of the following pathogens can effectively be removed by a typical sand filter? Sand filter has got relatively bigger pore size, so it comes under the primary or preliminary treatments. It doesn't go with the secondary one or tertiary or further. So it is a very preliminary kind of treatment. I'll go with the answers without further delay. So the answer is protozoa and worms. The bacteria and viruses are not visible in our eye, right? So they are in the they are called the microorganisms. Because why micro? Because micro means 10 to the power minus 6. So they go their size range is at the micrometer level. So they are that's why they are visible with the help of microscope. The micro term means 10 to the minus 6. So 10 to the minus 5 and 7, they are suspended kind of thing. So they are in the colloidal range. So they are not visible with the open eyes. And protozoa is also not visible with their open eyes, but it has got a size bigger than the your bacteria. So and virus is even smaller than bacteria. We know about bacteriophage, which is a type of bacteria, which is a type of bacteriophage or microphage, which is a type of virus that is used for the transfer of genetic material from one bacteria to other bacteria, right? And also it can destroy bacteria also. Sometimes it can be used as the bactericide or uh, antibiotic kind of thing. So bacterial infection prevention kind of thing. So these kind of diseases can be cured by using microphage viruses also. So nevertheless, the viruses and bacteria, these have got a smaller size, but the protozoa and worms means they can be just like earthworm. So the worm means they are visible in the naked eye, and they can obviously be separated by using a typical sand filter. Okay. Okay, so let's go to our next question. So there is a statement. Statement one is total coliforms are present, are a possible indicator of chemical contamination. And statement two is germ theory states that certain diseases are caused by the invasion of the body by microorganisms. Those are too small to be seen except through a microscope. The thing I was telling earlier, the term micro means 10 to the power around 10 to the power minus 6, that means 10 to the minus 5 to 10 to the power minus 7. The size ranges within this meter. So that means they are not visible with our open eye and can be seen with a microscope. So the statement is correct, but whether germ theory states that or not, that you have to tell. So you have to identify that which of the following statements are correct. So the first one or second one or both are correct or not. So you can type your answer in the chat box. I'll encourage Santosh and another. What is his name? Santosh and Abid. Shaikh Abid. Shaikh and Santosh, I will encourage you to also to answer. This is not a evaluation session. This session is just for practice. So don't be shy away from answering if you are watching. Okay, nobody is coming forward with courage. So I think I'll have to answer the question. Because statement one is incorrect. Orchana is saying total coliforms are. I think it is you have stated it correctly, because coliforms is something, your coliforms is what? Coliform is some pathogen, right? Some bacterial organism. So it is not an indicator of chemical contamination. It is obvious. So it is obviously incorrect. And statement two, maybe you don't remember the germ theory. It's okay. So I'll tell something. So there is coliforms. So the term is related to what? So the amount of microorganism that is present inside the water. Statement 2 you are saying is correct. Program is telling it is correct. Okay. So the term coliform is related to colony formation, right? And also E. coli bacteria. So these coli colony, these are similar actually. Their origins are almost same. So there is the unit with which they are measured. The presence of bacteria they are actually measured, is CFU. Is termed as CFU. That is called as colony forming unit. And they are so if the water is taken, the biotechnologist actually collects the sample water and they actually incubate that water, and they probably, I don't remember, they use certain medium like from gelidium, agar agar, these are kind of what is called as they are nurturing for the bacteria. And after certain time, if certain amounts of CFU or colony forming units amount of bacteria is visible, then actually they will say that yes, I mean, um, we can confidently say that yes, there is indication of biological contamination in the water, right? But it is obviously not a indicator of chemical contamination. And so yes, so it is a possible indicator of the fecal contamination that is present inside the water, because what I earlier said that Escherichia coli, yes. So E. coli, it is a good bacteria, right? Yeah. It is a bacteria that is present inside our guts, and which helps for digestion, right? And also if it is I mean, if it is more more in quantity than what it should be, then one get diarrhea also. So in a balanced quantity it should be there. So you are say a bit wrong, I think. So E. coli is not that beneficial bacteria. It may causes other diseases also. The good bacteria is your lactobacillus trichotis, which is present inside our guts. And also by the intake of yogurt you can get this bacteria in your digestive system, and it can improve your digestive health. So E. coli is not that much desirable, and if it is an indication of your fecal contamination. So fecal matter you can relate it, I think. So that's why it is an indicator of biological contamination. And whatever germ theory is studying, that is correct. So the statement, which is obviously correct, it is stated by the germ theory only. Okay. Now the term germ, you can understand that. So the germs means the organisms which we cannot see in our naked eye, right? So statement 2 is correct, and statement 1 is incorrect. Both of you have stated it correctly. Now let's go to our next, again MSQ, multiple select question. So you have to select the correct statement regarding the acceptable limits for drinking water in the Indian standard. So the Indian standard, or IAS, that gives you the acceptable parameters for drinking water is 10500. So I think 2012 is the latest version. I don't remember exactly, but it is widely used. And what is the correct statement regarding the acceptable limit for drinking water as per the standard? So option A is pH range 6.5 to 8.5. Option B, TDS. TDS is the total dissolved solid. That must be less than equals to 700 milligram per liter. Option C, total hardness less than equals to 200 milligram per liter. And option D, nitrates less than equals to 55 milligram per liter. I will give you 2 minutes to come up with the correct answer. You can type your answer in the chat box. Okay. Progyan is telling A is absolutely correct. Yes, it is obvious because whatever we drink the water, it should not be acidic and it should not be highly alkaline or basic because uh, otherwise it will harm our inner wall of our what is called food duct or digestive tract, right? So A is obviously correct, and you are telling at 500 milligram per liter. What is it? It is not in the option. So which one you are telling? TDS or total hardness? I'll say so I'll comment a bit on that. So the thing is that the TDS is the total dissolved solid. Dissolved solid means you can understand the matter which is dissolved in the water. It is the total count of that. Dissolved means again which is, you just got particle size less than 10 to the minus 7. For example, sodium chloride, monovalent ions. Their particle size is far less, so they are actually dissolved. Total hardness is actually a part of the total dissolved solid. So hardness is caused by the bivalent ions. For example, magnesium chloride, calcium chloride. So their particle size is a bit bigger than the uh, monovalent ions like sodium chloride, but they are still dissolved in the water, right? So if you heat the water or if the water is um, stagnant for a long time, then you will see a white layer on the utensil on which the water was kept if the hardness is high in that water. So that is the component of the TDS basically. And the nitrates is less than 555 milligram per liter. So which one is the acceptable range? TDS limit is 5 minutes. Okay, okay, you are saying that. So B is obviously you are saying it is incorrect, right? And then C, I think it is correct. I also don't remember. Let's see what is the correct range. So yes, you are correct. TDS limit, whatever is given, it is not correct. And but the hardness and pH range is correct one as per the Indian standard for drinking water. There are also international standard, WHO standard, more or less same for drinking water. Okay, Santosh and Shash. Okay, Sadik has left, I think. Murugeshwari has joined. So you can also answer. Don't feel shy away. It is just a practice session. Okay. So we will get with our we'll go with our next question. So I'll comment on something. It's just for your knowledge. There is some concept that is told as economic water scarcity. So what is it? There are people, there are source of water, and what may happen? The water, the source may not be adequate for the people that is present in a particular region. This is called as the water scarcity. But what may happen to supply the water from the source to the people? Uh, manage proper management or infrastructures must be there. Let's assume there is a good source or good amount of water to supply to cater the need of people of a particular region. but due to improper management or infrastructure, the water from the source to the people that is present in that region, they are not getting the water. The water is unable to be supplied from the source to the people. So there is a scarcity of the water due to the improper management or infrastructure. This kind of water scarcity is called as the economic water scarcity. So this scarcity is related with treatment, because there may be the treatment facility that is needed, because the source water may not be directly consumable by the people, right? So the treatment facility or treatment technology that may be insufficient. Maybe the treatment technology has not been developed to treat this kind of water that is present in the sources of water, right? Like water bodies or whatever. Or it may so happen that the technology is there, but the economic or financial background of the government, or the local body is not sufficient enough to implement that technology for the supply of the water. So it may be management issues or infrastructure also. So all of this, if because of this reason, even if the source is present and people is present and the water is not being supplied, then the water scarcity created by these kind of reasons is called as the economic water scarcity. Now we'll solve a problem which will clarify your concept regarding hydraulic retention. Okay, so let's say there is a lake in a city called Bhopal having approximate volume of 5 into 10 to the power 11 meter cube with an average annual outflow of 0.7 into 10 to the power 10 meter cube per year. Then you have to calculate the HRT, that is called as the hydraulic retention time for the lake to the nearest integer. Option A is 70 years, option B is 72 years, option C is 74 years, and option D is 76 years. If you know how to calculate, then you can calculate it. Just you don't have to take any notes. You can, for the sake of calculation, you just simple problem just to clear your concept of hydraulic retention time, because later we will be solving certain other problems which has got a deeper concept, and the concept of HRT will be required for solving the upcoming problems. It is very simple. So I'll just tell you something. Um, so if you have watched the lecture, then you will be knowing. If you don't have watched, then just listen to this thing. So if you consider there is a tank and it is the water inside the tank is completely mixed. Flow is coming in, flow is going out at the steady state condition. Steady state means the flow that is incoming is equals to the amount of the flow that is outgoing. So the height or the amount of water that is inside the tank is not varying. In that case, the hydraulic retention time will be the volume of the tank divided by the flow out or flow in, because both are equal, right? Here in our problem, the tank is nothing but a lake and the lake is nothing but a tank, right? And there is another concept that is called as solid retention time, or in certain cases or certain scenarios where activated sludge process is employed for the treatment of wastewater, then it is called as the sludge retention time. That is equals to the mass of solids that is present inside the tank divided by the mass of the solids that is leaving. So there the solids may not be incoming. So Activated sludge means basically the sludge, the bacteria that is present inside the water, that is the bacteria that is present inside the tank or the sludge, that is activated. Activated to do what? Activated to treat the water, activated to treat the BOD content, that is the measurement of the biological biodegradable compound that is present inside the water. So as the time passes, they consume the pollutants that is present in the incoming water, and they grow in numbers. So there's certain, at a certain rate, they must be taken out also. Otherwise, they will form chunks of biomass inside the water and they will float, and you will see froth floating on the surface of the tank, right? So they are the mass of the solids that is living. With that amount, you have to divide the mass of the solids that is present inside the tank to get the value of the solid retention time. But however, here you have to calculate the HRT. So the residence time is the average duration of a particle of water to pass through a phase of hydrological cycle. So here, in case of our lake, the HRT is 5 into 10 to the power 11 meter cube. That is the volume of the lake divided by 0.7 into 10 to the power 10 meter cube per year, which is 71.43 years, right? So option B is correct in our case. Has anyone calculated? Hydraulic residence time and hydraulic retention time is same. Why, I will tell you again. So it's a good question. Residence means what and retention means what? You are considering a particle of water. This term is important. So the water is flowing. You are just analyzing a particular particle of water, right? So particle of water will come in, stay and go out. So it is residing inside the tank, as well as it is actually your residing and retaining. So you are retaining the water. So some particle may come and immediately go out. Some will stay for longer in the dead zones of the tank, and then again it will go out after a very long time. So if you take all the particles, then if you plot their time that they are spending inside the tank versus the amount of the frequency, their frequency. So if let's say you are tracking the residence of the water particle with the help of uh, some color. Let's say you injected a color here, color, or let's say you injected radioactive particles here, and you are tracing their radioactivity at the output. Then over time you will get a Gaussian curve. Okay, so you will get a Gaussian distribution. So the highest number that actually will be spending by most of the particles present inside the water. But in case of solids, you have to retain them. So here solid actually basically they are acting as the tracer for the flow of the water. So how they are flowing, if you are able to observe the solids inside it, then you will be able to understand the concept. So here the retention and the residence basically means the same for water. But yes, for the solids, basically the retention term is more used. But even sometimes if SRT, some books, if they are stating it as residence, then also it's okay, because you will understand that in that case they are considering both the solid in and solid out. So if you take a mass balance and there is no change in the height of the water inside, then the mass that is flowing in, that will be equals to the mass of the flowing out. The form of the mass, the chemical composition of the mass, that may get changed, but their amount will remain the same. So that's why, In the both the cases, be it a water or be it a solid, hydraulic means water basically. So the residence and the retention, the terminologies are basically same. Okay. Uh, yes, we'll come into that concept. So volume by discharge. So this we will come in a few minutes. In some following problems, we will come in those concepts actually. So there is a concept of space time, and that is equal to the HRT here. So we will come into that after a bit. So the next question is the rate of reaction depends on which one of the following. This is an MCQ type of question. Option A is product, option B is reactants, option C both of the products and the reactants, and option D is none of them. Basically, some term must be added here. The rate of the reaction generally depends on which one of the following. Okay. Option C, you are telling both products and the reactants. And Progan is telling C and Orchona is telling us reactants. Hmm. Any other? Santosh and Murugeshwari has left, I think. Okay. Uh, Mohan has joined. Okay, so Mohan, go ahead. Can you answer? So option A, I think the answer is incorrect here. That's why I added the term generally here, because the rate of the reaction generally depends on the answer is incorrect, I think. So okay, sorry about that. So think from wherever it is taken, yeah, given it incorrectly, so it will not be product. So I'll talk about this a bit, and I'll correct it. Okay. Okay. So basically, the rate of the reaction depends both on them, both products and the reactants. But if generally stated, then it will be the reactants. So all of you who have answered it is correct. There is an exceptional case where the let's say let's take some pen. Let's say there is one component A, and from A there are two types of reactions are taking place. One is giving you B and another one is giving you C. Let's say this B thing is your desired product and C is your undesired product, let's say. Okay. So now why it is undesired? Sometimes it may happen that A is the reactant, right? And C and certain catalysts are being used for the reaction, so that you get more and more the desired product. These are called as the parallel reactions. And C is undesired. Why? Because it acts as a catalyst poison. And also sometimes it may, even if it is not a catalyst poison, it is one example. Another example is that C may act as an inhibitor or a feedback kind of thing. So it may reduce the reduce the yield of the product B. Okay. So in this case, product will influence the rate of the reaction from A to B, right? So it is not a general case, but if generally is mentioned, then you have to give the answer B. Otherwise, you have to give the answer C. So both of you have given correct answer. Okay. So all of you. So now the thing is that uh, can you give me some example of this feedback mechanism in our body? Uh, anyone? Are you from biology background? There is. I'll tell you something. So we have our pituitary gland in our body, right? And we have thyroid gland. So from thyroid gland, there are certain hormones like T3, T4 are secreted, I think. Yeah. And from pituitary gland, some stimulating hormone is secreted, which actually basically increases your secretion of the thyroid gland, the T3, T4, thyroxine and triiodothyronine. These are T3 and T4 hormones, right? So it has got certain functions in our body. So if the amount of the hormone increases T3, T4, then it is called as the hyperthyroidism. If it is less, then it is called as hypothyroidism. So if the amount of the thyroxine hormone increases, then we have got certain problem in our body. But in a feedback way, the increase of the thyroxine decreases the hormone that is getting secreted from our pituitary gland. Yes. So it has gotten certain feedback loop. So the reason for which it is getting generated, it is actually violating that reason only. It is preventing its reason only. So it is an example, ideal example of how product is inhibiting the rate of the reaction, or it is inhibiting the formation of its. I mean, even it is not even the product C. It is one-way reaction only, A to B, and B is actually preventing the its own generation by means of its. I mean, the increasing concentration in our bloodstream. Okay, and also there is one example. You have also studied it. Those of you who are from chemistry background, or and also not even chemistry, even if you had science in your +2 level, there was one principle called as the La Chatelier principle, right? So in the according to that, if in a closed system. My God, just got lost. Just wait, give me a minute. Please excuse me. Okay. Okay. So, uh, where are I? Hmm. So I was talking about the last atelier principle. So in that principle, if there is a closed system and within that system the product is getting more and more generated, so in a way it will basically prevent the its own generation, right? So the equilibrium will shift from the right side to the left side. But there is a concept of dynamic equilibrium. That means the amount that is the rate of the forward direction is equal to the rate of the backward direction. So you don't see a net change of the concentration. That is also there. Okay. So now we'll proceed to our next problem. Okay. Okay. So I think it is 8:05. So we'll take a 5 minutes break and we'll rejoin the same link uh, around 8:10 sharp. So you can take a small bio break, and you can again rejoin in the same link, or otherwise I am available. You can ask a question or doubt um, about whatever we have discussed until now. Um, okay, otherwise we will join at 8:10 sharp. Any doubt you may ask. Dhananjay has joined now. So we are taking a small break. We'll join around 8:10.
Okay.
Dhananjay, if you have watched the previous lectures recording, or if you have attended the last class and having any doubt, then you can ask either by unmuting yourself, or you can type in the chat box. Otherwise, we'll resume the session.
Yeah, please resume the session because I've not seen the last video.
Okay.
I was occupied in an office call, so I missed even today's 1 hour session, I'm sure.
Oh. Can you please tell your background? I mean, from what you have done in your bachelor's or master, or you just studying bachelor degree?
So I completed my bachelor's in mechanical engineering in year 2006, and after that I joined paper industry, and then I
Oh,
worked with
great.
on the projects of Times of India,
Okay.
expanding their printing in units and all.
Okay.
After working for 4 years, I came back in plumbing and fire protection design.
Oh.
And right now, I'm doing the fire, majorly the fire engineering for US region. Apart from that, I'm doing medical gas, plumbing
Hmm.
design.
Hmm.
And since I'm in plumbing, so this is one of the subjects I'm really interested, and I was trying to learn, but nobody explains you.
Yeah.
Everybody goes to the vendor, like, okay, do the calculation, go to the vendor, this is my total flow, and after that he will be deciding what type of system he will use, what will be the membrane size and all.
Hmm.
And when I saw this course, so the only thing came into my mind was like, maybe now I will be able to do all those calculations my own.
Yes, yes, yes. Absolutely. So keep in, I mean, uh, keep in touch with that. The
Let me
lectures
mute
are
myself.
those are being uploaded in the NPTEL website by and those are delivered by Dr. Bhelanki, and I mean, watch them regularly, and definitely you will be able to do that.
Definitely, I have to go through those videos. I missed a couple of them just because of some workload and
Mm.
all. So
Yes.
now I have to come back and check all these things.
Mm. Okay. So let's resume.
Thank you.
Uh,
Yeah,
mm. Now, I think my screen is visible. Sorry. There is a good book on designing an effluent treatment plant, which is based on MBR systems, that is membrane bioreactor and activated sludge processes. So it is Medcap's book, I think. Medcap is the name of the writer, I think. It is a very good book for ETP design. And for membrane design, because membrane is a hot topic nowadays, and my research area is also membrane, many books are coming on that. Uh, there is Professor uh, uh, Prasanna S. Mudal, Prasanna Kumar S. Mudal. He is a professor of IIT Bombay's Material Science Department. So he has written a good book on membrane technologies also. And there is Professor Porimal Pal of National Institute of Technology, Durgapur. So he is working on the water. He has written a good books on that also. And also, Sir Dr. Bhelanki, who is an environmental engineer. He is teaching the course also. He has also done a great contribution on this sector. So if you go through his research areas, research papers and all, so it is a good source of knowledge on this area. Okay, so I'll encourage you to go through this material. And okay, so our next question is, it is a column matching. So in the left hand column there are batch reactors, PFR system, and CSTR or MFR. These are sorry about that, it is not reaction time types, it is reactor type. Okay. uh, okay, so you have to match the reactor types with their definitions. Option A is reactors in which fluid flows such that the fluid reactants are not mixed along the direction of the flow of the fluid. Option B is reactors with zero mass flow in or out of the system. And option C is homogeneous reactors with mass flow in and out of the system. So keeping the left hand order same, you can just tell me the correct right hand order. You can type in the chat box. 4 people are there: Archana, Dhananjay, Progyan, and Monohar. Any one of you, just type the correct order in the chat box. I hope the question you are understandable. So in the left hand side there are types of the reactors, and the right hand side there are their definitions are provided. You are saying Archana is saying as BAC. C is CSTR or MFR. Both are actually basically means the same. CSTR means continuous star tank reactor. MFR means mixed flow reactor. The starring causes the mixing, so it means the same. Sometimes it is also called as CMFR, continuous mixed flow reactor. All their meaning are same. The plug flow reactor is a different thing. The batch reactor is a different thing. And I think Archuna's order. Anyone else has given? Okay, I think Archuna's order is correct. So batch reactor means reactor with zero mass flow in and out of the system. PFR means reactor in which fluid flows such that the fluid reactants are not mixed along the direction of the fluid flow of the fluid, that is the axial direction of the fluid. And option 3 is CSTR or MFR, which means the homogeneous reactors with mass flow in and out of the system. Next is you have to identify the incorrect statement from the following. It is an MCQ and the options are: option A is in a CSTR or MFR, the concentration of the reactor is same as the concentration in the effluent from the reactor. Option B is composition is identical everywhere inside a MFR. Option C is in an ideal PFR system, concentration must not vary radially. And option D is none of them. Anyone? Who you have? I mean, most of them are correct. You have to identify the incorrect statement. Later we'll go deeper into these concepts. What this mixed flow, plug flow, batch flow. What is the meaning of them? We'll go a bit deeper into them. Let's see what is your preliminary understanding on that. So Mohan is saying option A is the incorrect statement. CSTR the concentration must not be the same. The inside the reactor there is one concentration, and outside whatever the effluent that is coming out of the reactor, that has got a concentration, and you are telling it must not be the same in case of CSTR. Okay, anyone else about the incorrect statement among them? No one is actually making the obvious mistake, which I want you to do, and you are not even answering. Okay, Archana has said option D. Anyone else? Yeah, your Dhananjay and Progyan. Your name is Progyan, or you have joined through your father's account or something? No one is coming forward. Okay, I will tell the answer. Okay. It's okay. Regarding the answer, which one do you think it is incorrect? Anyone else joined? No one else joined. Okay. I'll explain. No issues. Other maybe I mean Sad has discussed them in lectures. Even if you have not watched, I will make them clear. Okay. So the thing is that option D, none of them is the correct. Actually, it is actually all of these statements are correct. Option A, B, and C. I thought some people who have studied it, they will say C as the incorrect statement, but nobody made that mistake. And Archana said it correctly. All of these statements are correct because in a CSTR and PFR are almost are the same thing, and the composition is identical everywhere inside the MFR or CSTR reactor. Now, whatever is the composition of And now we'll see. And now you can look at the third statement also. In an ideal PFR system, concentration must not vary radially, and it should vary axially, right? So we will see a picture of various type of reactors. Uh, where is the picture? It has gone. Arey yaar. So the picture is not coming, unfortunately. Mhm. Just wait. Just wait. Okay, it has got some problem, I guess. Just wait. Sorry about that. Yeah, it has come back. Yes, it is there. So sorry about the problem, and thank you for your patience. No. So these are the various type of reactors. So number one is the batch reactor. I hope my screen is visible. Number two is your CSTR, that is MFR or mixed flow reactor or constant start tank reactor. Okay, Dhananjay, you also don't know. I'll be telling you the thing. The third one is PFR or plug flow reactor. Okay, what does this mean? These are their design equations, where V represents the volume, T represents the time, F represents the molar flow rate, X represents the fractional conversion from the reactant to the product, and Ra is the rate of the reaction with respect to the reactant. Here, reactant is the pollutant. Okay. So, if the reaction rate can be represented in terms of product also, that what actually indicate gives some direction to our earlier MCQ, where there was they are telling about the rate of the reaction. It depends on the product or the reactant or both, where it was asked. So rate can be represented in terms of any one. Now, what are these type of the reactors? So this is BR or batch reactor, this is CSTR, and this is plug flow reactor. Now, if you look at the earlier MCQ, so in case of CSTR and MFR, they are basically flow reactors. So feed is coming in and effluent is going out after treatment. There is one starter. That's why the term start tank reactor is there. The tank is there, starter is there. Starred tank. Okay. And continuous. Why continuous? Because flow is coming in continuous, flow is going in, going out continuous. So this is a concept of chemical engineering basically. If the flow in and flow out is equal, then they are called as a steady state. The height of the water or whichever that is present inside the tank, that does not vary with time. If that varies, then it is unsteady state. Okay, but in both the ways, water is coming in and water is going out continuously. So that's why it is continuous flow reactors. PFR is also a continuous flow reactor because flow is coming in, flow is going out. Now, here in the case of the CSTR, the flow is completely mixed inside the reactor. Okay, so that's why it is in ideal condition, it is ensuring that the concentration of the pollutant or whatever species inside the reactor is same all over the place, and that is also going out. So that's why the concentration of the effluent stream that is going out and concentration of the same species that is inside the reactor everywhere, they are the same in case of either MFR or CSTR. So that's why both the statement A and statement B was correct. And in case of PFR system, it is saying that concentration must not vary radially. Radially means what? If you consider it as a cylinder, and then it will be its radius or diameter or whatever, and it is its axial direction. So there is a plug basically. You are introducing the element, fluid element is flowing like a plug, and within a particular plug along the radial direction, there must not be any variation of concentration. But along the axial direction, the concentration, that means from plug to plug, plug of a particular fluid to plug of a particular fluid. If you imagine a particular plug of a fluid, plug means what? It's an imaginary control volume which is flowing through the in the axial direction. So in the axial direction, there will be variation in the concentration. For example, if the concentration is Ca naught here, let's say a particular component, particular pollutant is Ca naught, and you are treating that pollutant inside the plug flow reactor, it should, the concentration of the pollutant should vary in the axial direction, but it should not vary in the radial direction. That means if you consider a particular imaginary plug of liquid, that is a small CSTR. So PFR is a combination of infinite number of CSTRs or MFRs in its axial direction. Okay, so both the CSTRs and PFRs are continuous flow reactor because flow is coming in, flow is going out. But the batch reactor, you put certain amount of liquid, then you stop the inflow, you treat it, then you open the valve here and you discharge the liquid. That's why it is a batch operation. So that's why it is called as the batch reactor, batch by batch. You taking in the fluid in, you closing the lid, you are treating it, again you discharging, emptying the tank, again you taking the fresh batch in. So this is called as the batch reactor. That's why the others are continuous flow reactor. There are two types of mainly continuous flow reactors. There are also other types like packed bed reactor, fluidized bed reactor. Many other types of reactors are there, but these are the main two types based on which we will be solving problems. The upcoming problems we will be solving based on these three only. So the batch reactor, the CSTR and PFR, I think you are able to visualize their flow pattern, right? Because their name is based on the flow pattern of the fluid inside them. Okay, so if you have any doubt regarding the understanding of the flow, whether it is mixed or not mixed, why the name came, so if you are still having certain doubt, you can ask. This is the time for you to ask.
Yeah, yeah. So Santanu, like I raised my hand. So when we are saying like the constant flow, like this CSTR, so concentration of the fluent inside the reactor as well as going out of the reactor is same.
But the feed
So
concentration is different.
why? What is the purpose of this?
The purpose, see, CSTR and
Okay, so
PFR
feed concentration. Okay,
feed
please go ahead.
concentration is different. The thing is that this CSTR and PFR, they represents two ideal scenarios. They are just like the two poles. But in real condition, the reactor is neither CSTR or not PFR. They acts in between. So there is an amount of mixing that is happening inside the reactor. There is a particular dimensionless number which represents the amount of plug flow or amount of mixed flow. So whether it is towards the mixed flow or whether it is towards the plug flow, there is a particular number actually which actually determines the back mixing of the back mixing, the quantity of back mixing of the fluid that is present inside the reactor. So there is no purpose basically. The CSTR and PFR represents two end poles of the types of the reactors, but in reality no reactor is ideally CSTR or ideally PFR. They are actually in between. So why these concepts are introduced? These concepts are introduced for designing purpose. So let's say there are certain orders of reactions, right? So there are first order, second order, third order. We will come into them after a while. So you can see the red term RA, right? Okay. So you can see the red term here. So the rate means reaction rate. RA equals to K into C. C is the concentration of the reactant, let's say. So the CA, so RA may vary, may be proportional to CA to the power 0. CA, that means it does not depend on the concentration at all. It may depend on the CA to the power 1. It may depend on the CA to the power 2, like that way. So it may be first order, second order, like that way. So depending on the rate kinetics, CSTR, in some cases CSTRs are preferable. It gives more yield, and some cases PFR gives the more yield. It is inherent in the design equation. If you solve the percentage conversion, if you get that, let's say 0 to xt, so it is converting, let's say 30%. So depending on the order, some for some cases of the reaction rate kinetics, CSTR will be preferable. It will give more yield than the PFR. In some cases, PFR will give you more yield than the CSTR. If you consider volume wise, for the same yield, depending on
My
the
question is different,
okay.
Santanu. So my question is like, if it's continuous flow,
Mm,
and one is the batch where you just stop the
mm,
effluent, then it settles and all those processes happens,
mm.
maybe the bacterial or whatever the things happen. But in continuous flow, how we are controlling that? Like, if we have to do the bacterial treatment, or we are adding air in the effluent and all those things. So how we will be controlling that? Like, exactly how it is being happening? What is happening inside the reactor when we talk about CSTR or PFR?
Yes, it's a good question. So basically, uh, I mean, it is a chemical engineering concept. So if you are from chemical engineering background, it will be easier for it to understand. So there are different types of control systems that those are in place, either feedback control system or feed forward control system or cascade control system. What it does, it actually measures the, let's say it is a feedback control system. So it is continuously measuring the dissolved oxygen content at the outlet. There are various type of control mechanisms that can be employed here. So I am giving a very simple example. So let's say it is measuring the control at the outlet. Okay, and there is a
Okay.
jacket outside the, let's say, for a party the reaction rate, that is there are bacteria present inside the reactor, and they are
Yes.
converting certain pollutants into its products that is less harmful. Let's say they are degrading complex hydrocarbon into simple hydrocarbons. Let's say there are certain kinds of specialized bacteria, those are present inside the reactor. So but their reaction rate is higher at a particular temperature. Let's say they give the highest yield at the 50 degrees centigrade, and you are continuously maintaining the temperature, hot water temperature that is outside the reactor at 50 degrees centigrade with the help of hot water flow. There may be jackets, there may be limpets, there may be coils, and there is a temperature controller that is present at the outlet. So if it senses that the temperature is going down, it will increase the hot water flow at the in the jacket to maintain the optimum temperature. If it sees that it is exceeding the optimum temperature, it will the control valve will be closed so that the amount of water flow gets decreased. It's a very simple example that how the temperature is maintaining. There are also other type of, let's say, certain chemical is being dosed uh, inside the reactor. So there may be certain control system to control the amount of doses also. So to understand that, these are just the preliminary concepts. You have to understand the design equation, how it is related with the volume. Then it will be put into certain control system. So for better understanding, I will suggest you to study this book. It is Chemical Process Control by George Stephanopoulos. So it's a very
Can you just name that book in the chat box, Santanu,
yeah, yeah.
if possible?
So it is very good book for understanding the control systems, but for they are very hard concepts. To go there, first you have to
Uh, and to be
yes,
honest, I'm in job, so if there is only one book which I can refer to get more knowledge, that will be more helpful for me
yes, Ravi.
because we are mostly concentrating on the results now. Before
Hmm.
10 years or 15 years, we were in the condition where we were looking for the knowledge. Now we just look for the results. So
Yes.
any one book which is having all this knowledge, so that will add more value to me.
So I have typed that name of the book in the chat box. So these books
Yeah,
actually
I can see.
gives you the comprehensive knowledge of the control system. There are certain mathematics are involved. There are control valves, so how they are working. So they are very, I mean, their response time is very high or low. Depending on that, you will get the output. So if you imagine let's say a pharmaceutical industries. So if there is, I mean, the product is very costly. Let's say they are harvesting the enzyme that is being generating in a bioreactor. So if the control response time is very high, that means if certain changes is being occurred, and within that time, whatever the product is being generated, that becomes off spec, and that becomes a loss for the industry, a high value loss. So they cannot afford that. So their control system must be very specific, very sophisticated, with a very high response time and all that, and also the response time must not fluctuate. So it should get dampening should be there, so they should get stable. So all these concepts will be there in the book, but to understand that, because these type of equations will also be there, to understand that the basic design equations of these types of reactors, first you have to understand, then the studying of the book I'll be recommending. But yes, that's all. There are after the reaction kinetics, there are advanced theory. So advanced chemical reaction engineering are there. So which deals with the basically the research areas which are still open-ended question on this sector. But to understand the control system, this is a very good book, I'll suggest. And as far as the water treatment is concerned, so precise control is not required, but you will see diometers are there, online diometers. So as just I told the example of temperature and dosage control. So there are diometers also, which determines the
Yes,
uh,
that I have seen.
what should be the aeration rate inside the sludge treatment plant and all. So you are experienced, so maybe you will be understanding these things, but other people maybe they will not be understanding
Yeah,
whatever.
practically I have seen this in effluent treatment plants. So
Yeah.
they had this and dosing machine, and that was
Yes, yes, yes.
uh, putting the chemical based on the requirement after certain time. But I
Mhm.
was not sure like how they are calculating and all those things. So
So what they do sometimes, the industry are not very advanced. They take the sample after, let's say they maintain a shift report kind of thing, and after certain interval of time they check and they plot. like that way. Point wise they plot, after 1 hour or 2 hours they take the reading and they plot, and they see how the parameters are varying, and accordingly they changes the decision, because it's an effluent treatment, so it is not a product based. So product specification must be very I mean highly controlled. But there may not be in effluent treatment case, there may not be any online meters present. Maybe they are taking the samples, testing in the lab, and they are plotting the data like that way. Or maybe shift wise they also take maybe 3 or 4 times a day also they take the sample like that way they do. As per my understanding, I have also worked in on the companies, so they are
Exactly, this is what they were doing. This is what they were doing, and based on that, they were increasing or
taking some
decreasing the
decision. Yes.
dosing.
So as the more and more the environmental norms become stringent, so maybe in future government may demand zero liquid discharge plants is a concept, new concept. So there you are not discharging the liquid, but if it is not discharged, it is if it is being discharged, then government may demand in the future that you have to install online systems there, so mandatorily, so that we can take the data online and in a continuous manner, not in a very uh, distinctive way that two or three times a day, not like that. So these demands may come in the future, but currently in the countries, developing countries like India, this kind of stringent norms are still not there, but it may come. Okay. Uh, okay. So any other questions? Any other one? So regarding the concept of the reactors, so we'll be actually the time is also very less today, so we'll be solving on a good problem based on that. Um, so you can always ask if you are having any question. Okay. Now we'll be going with our next thing. So you see these equations. So how they come into the picture? They come by simple mass balance. Mass balance means so there are various systems like batch reactor, CSTR, and PFR. I will be telling mass balance of a simple batch reactor. The general mass balance equation is something like this: rate of accumulation of mass of component A in a particular system equals to mass flow rate of the component A into the system minus mass flow rate of component A out of the system, plus rate of generation of mass of the component A from reaction minus rate of depletion of mass of component A from the reaction. It is a very general concept. Let's say I have taken a particular batch reactor and I am doing mass balance analysis for that. There is a mixture and all. So the let's say there is a water and there is a particular component. Let's say I am measuring the dissolved oxygen. So mass of component A, that is the dissolved oxygen in the water I am measuring. So the amount that will get accumulated, what is that? So there will be coming in and coming out. So in minus out, if in is more than out, then in minus out gives you positive accumulation, right? Plus generation, if there is certain generation of from some other species, A is getting generated, minus the rate of depletion, so A is getting also depleted, A is converting into other species. So the concentration of A inside this system is the summation of this. So flow in minus flow in of A minus flow out of A. So let's say over time some amount of A got accumulated inside this. Then what will happen? There is one inflow, and for continuous system there will be inflow, and for continuous system there will be outflow, and there will be concentration of A inside the inflow system, and there will be concentration of A at the outflow, right? So if A in the stream that is coming in has got high concentration of A, the concentration of A inside the tank will increase over time. Do you understand this equation? So any doubt? regarding this simple equation, you can either type in the chat box or you can unmute yourself and talk. Okay. Now, our case is a batch reactor. So, mass flow rate of component A into the system becomes 0. And mass flow rate of component out of the system as well as the rate of generation of mass of component A from the reaction becomes 0. Why? Because we are not generating pollutant. We are degrading the pollutant into some other species. So here, the accumulation becomes the depletion. That means your negative accumulation. It is not accumulating, it is basically you're depleting. The rate means what? If you divide the terms by time, that becomes a rate. The rate of accumulation of mass of component A in the system becomes the rate of depletion of mass of component A from reaction. This is the reaction. RC equals to dC by dt. dC is the component. This is the concentration of the reactant A. That is the amount of change that is occurring in the concentration over time, that is equals to the rate of the reaction, right? So the Q into C dot minus Q into C, these are basically your flow in and flow out. This becomes 0 here. And V is the volume of the reactor. Volume into concentration gives you the mass. This gets cancelled out. That gives you dC by dt equals to RC in case of batch reactor. If you take a first order reaction, then RC becomes K into C to the power 1. This 1 is your order. It may be second order, it may be third order. Okay. Now K into C, this C you bring into this side. It becomes dC by dt equals to, as A is getting depleted, rate of depletion. That's why there is a negative sign. It becomes minus K into dt. This dt comes at the right hand side. And then you integrate it from C0 to Ct, and here in the right hand side you integrate it from T0 to Tt. Now those of you who, most of you are having mathematics background in your plus 2 level, so you know what is integration differentiation is. If you don't know, then just you have to memorize this formula. That's what I can say, because it basically, because I cannot go into the concepts of integration. So it is basically, it demands, the course demands the basic mathematics knowledge of integration of plus 2 level, unfortunately. So now after integration, there is a formula of integration. It becomes ln of C equals to minus K into T. Ln of C means it at the right hand side it becomes e to the power minus kt, and ln of C minus ln of C naught becomes ln of C by C naught. So this remains at the left hand side. So the ultimate mass balance equation for batch reactor for first order reaction becomes C equals to C naught into e to the power minus kt. Okay. But this is for batch reaction where the mass flow rate in, mass flow rate out, these are 0. For continuous flow reactors like PFRs or CSTRs or MFRs, as I told earlier, there the term that is stated T here, this T becomes hydraulic retention time or theta, or T naught. It is expressed as T naught. So what is it? Here there is no flow. So the concentration that is changing over time, and the water is present inside it. No, nothing is coming in and nothing is going out. That reaction is given in your batch system. But in case of continuous system, it becomes space time. Why? Because there is continuous flow of water inside and out. So there, how the T naught is represented. So this T becomes T naught here, or theta. That is represented as reactor volume, that is the volume of the reactor divided by the volumetric flow rate, just like we solved the lake problem earlier. So this is termed as the space time. The time, space time is the space time is defined as the time that is required for processing one reactor volume of feed. If you increase the reactor volume, the space-time increases. If you decrease the reactor volume, the space-time decreases. If you increase the volumetric flow rate, then the space-time decreases. That is, it gets processed. The space-time actually becomes lessened, so it gets processed higher. But if you increase the volume, if you decrease the volumetric flow rate, that means slow flow is coming in, slow flow is going out, then the space-time becomes higher. I think it is clear to everyone. Otherwise, if you don't know integration, you have to remember it. Okay, so 10 minutes is left. We will be solving a problem based on these equations. So the thing is that this particular formula C equals to C naught into e to the power minus KT, this is applicable for fast order reaction and batch reactor. You see it here. The value of CT equals to C naught into e to the power minus KT. Okay. CT equals to C naught into e to the power minus KT. This is the formula for ideal batch reactor and fast order kinetics. Okay. Now, there are plug flow reactors, there are mixed flow reactors, and there are also zeroth order reaction, second order reaction, third and higher order reaction. So for them cases, the formula will be completely different because you have to take different boundary conditions here and you have to integrate, the integration formula will be different. So that's why we'll be getting different kinds of formula. So for the time being, for our problem, I will be telling you to these are called as the performance equations for different types of reactors. So these are the basic thing one have to study before going into the control aspect that is given in the book I just typed in the chat box. Okay. So for our solving problem, I will be focusing on the reaction of different types of reactors under first order kinetics only. So I don't know how much time I have. So I'll request you to be patient with me and solve the problem with me. Okay, so please write down these three equations if you are having a book with you. So for CT, for first order kinetics, the expression is C naught into e to the power minus KT. It is represented EXP in this way. It is also expressed e to the power minus K. It means e to the power minus KT only. For ideal plug flow reactor, first order kinetics, it is C naught into e to the power minus K into T naught. And for ideal CSTR or MFR, it is C naught into 1 plus K into T naught. These all three are the expression of CT. C naught is the initial concentration and CT is the concentration after time T. Okay. And it is first order reaction. That means R, that is the reaction rate, is represented at minus K into C to the power 1. In case of 0, it is C to the power 0. In second order, it is C to the power 2, like that way. Both of you have written it, I hope. This first order part, the first order formulas, these you have written. Now we'll be solving this problem before ending the session. So we have considered a batch reactor. Within that reactor, an experiment is run in the lab to remove propionic acid, which is a common organic acid that is used in the production of various chemicals. That is used in the production, that means it can be present in the pollutant water also. That is the effluent water that is coming out of the plant. Okay. That is what it is telling. And it is often present in industrial waste streams. Now, initial concentration, that is C naught in that equation, is given to you as 21 milligram per liter. And after 30 minutes, After T equals to 30 minutes, the concentration becomes 3.5 milligram per liter. The assumptions are steady state. That means flow in equals to flow out. And first order reaction kinetics. That means R loss equals to K into concentration of propanic acid. The rate at which propanic acid is being degraded inside the batch reactor is given by this equation, C to the power 1. So I think there is a one problem is that there will be a negative sign. Okay, so as it is loss, so that's why concentration is decreasing, rate is decreasing with respect to time. The problem statement 1 is, from the information given above, give an estimate of the reaction rate per second. You have to calculate the reaction rate. There are basically 3 problem statements. If I give you time to solve and think, I think I will not be able to finish within time. So I will quickly go through the solutions. You please go through the slides after uploading the lectures also. You can pause the video and watch, and also if you are having doubt, ask in the next session. We will be discussing them again. Okay, so we will be just using the first order formula that we just told earlier you to write down. So you have to calculate the reaction rate per second. The detailed solution is as follows. Applying the mass balance to a batch system, we get this formula that I told you to write down earlier. Ct equals to C naught into e to the power minus kt for first order system. The data given as input is Ct equals to 3.5 milligram per liter. C naught, that is the initial concentration, is 21 milligram per liter. If you put Ct here, C naught here, you will get, and T also after 30 minutes it is given as in the question. So you will get the value of the K. That is the per minute. Okay, as it is your 30 minutes, so that's why the unit of K will be per minute, because this must be unitless. So if you put the values in calculator, you will get this value. I'll be solving this problem again in the later class. I think it is a very hurried manner. For people who have studied this in advance, it will be easier for them, but for them who will be looking this initially, so it will be difficult for them. Okay, Archana is only there. Somebody has asked certain question. Okay, yes, okay, it is okay. All right, Dhananjay. So for you, I will be quickly going through. So Archana, how you are understanding this, or what is your feedback? So you are totally out of now, or you will understanding everything? I am just I am going very slow. What is your feedback on this? So I'll be just quickly completing this, whatever the other 3 statements also, and I'll be again repeating
It's
this.
clear.
Yes, please.
So it's clear.
Clear, right? Okay.
Data is given, we will put and the answer will there.
Answer will be good. This is putting the thing in the formula, nothing else.
Yes.
Okay.
Yes, sir.
And the second problem statement, it has been asked to, it is a batch reactor, right? Again, you have to consider a flow reactor. You have to calculate the hydraulic retention time in minutes. And again, the effluent concentration that you have to achieve. Here it is 3.5. Here it is 1.5 milligram per liter. It has been changed from 3.5 to 1.5. Now, from earlier, you have calculated this 0.0597 per minute. If you apply the mass balance to a plug flow reactor PFR system, then this formula basically changes. It is it is formula for a first order batch reactor. It is first order for a plug flow reactor. Just the T becomes theta. As I told earlier, it is your space time. It is normal time, it is space time. The theta value is what you have to calculate from the other values. The C theta is given as the you have to achieve this effluent concentration 1.5, and C naught is 21. The initial concentration is already given. By putting this value from here, we just get theta value as 44.2 minutes. And the third problem statement is taking you to consider it as a MFR. So first one is on a pH reactor, second one was your PFR, and third one is CSTR. Just like the three equations I told you to remember. And here HRT or theta is given as 50 minutes. So again, you just have to remember the formula. Okay, theta is given as 50 minutes, C naught is given as 21 milligram per liter, and by putting these two values, theta as 50 minutes, C naught is 21 milligram per liter, and K is taken from earlier value, that is 0.0597 per minute, you get the C theta as 5.27 milligram per liter. That's the answer. Okay, so I think we'll end this session here. I went a bit quickly at the last moment. No one else is there. If you are having any question, you can ask. Otherwise, we'll end. So
No, sir, it's all clear.
you just have to remember the formula and you have to solve the problem. That's all. Okay, so we'll end this session in a minute. If you don't have any question, and the things those have been discussed till now will be uploaded in my YouTube channel. The video will be uploaded there, and the slides will be uploaded in the folder, the link of which you will be able to get in your Swayam portal at the bottom, that is located at the left hand side. I show in the earlier. Okay, so bye bye, good night. We'll end the session here. Thank you.
Thank you, sir.
Oh, good night.